Hello, everyone. My name is Ahmed, and today I'm going to talk about federated random reshuffling, which is adapting the SGD without replacement algorithm for federated learning. This is joint work with Professor Peter Richterik, who is professor of computer science at KAUST, and Konstantin Mishchenko, who is also a PhD student at KAUST. This was work that I did as a research intern at KAUST as well. So the setting of federated learning is as follows. We have a server, and this server is connected to multiple clients, also known as devices. And here, these devices, we are going to assume that there are M of them. This is an exciting new setting for distributed machine learning because, as you can see, the devices here are often things like mobile phones or devices that are beyond the traditional paradigm of distributed learning. So this technology has been used in many applications and continues to be used today. For example, in Google Keyboard, in Apple Siri, and there are many other applications in healthcare and other areas. The challenges associated with federated learning is that we want our solution to be communication efficient, and we also operate under privacy constraints. So what that means is that we cannot assume that the bandwidth costs nothing. It costs a lot, and we need to use uh, as little data exchange between the clients and the server as possible. And also we need to preserve the privacy of each device. So what this means is that we cannot share data between devices. So for example, we cannot just ask any client to send its own data to the server. So the optimization formulation that we have is that each device has its own finite dataset. So for example, if we are building a classifier that can separate between cats and dogs, then device one has a few pictures and device two has a few pictures with their corresponding labels. And as in the picture, these devices, the data on them doesn't have to be balanced. So the number of data points cannot be the same. Here it is the same, but it can be different. Um, and the classes or labels can also be very biased on one client and so on. One client, for example, might just like taking pictures of dogs, so the entire data set may be of dogs on their device. But still, we want to learn something and to use this to improve our machine learning model. So we have a model, and given this model, each device can compute the loss on individual points on its own data set. So given a model that can predict whether an image represents a cat or a dog, the device can compute the loss with respect to um, uh, one data point that it has. And the data sets, as I said, can be very heterogeneous. They can be very different. So this can be abstracted away as this finite dimensional minimization problem, in which we have a function f that can be written as the average of these functions FIM. So there are m different nodes. So we have an average over each of these nodes here. So 1 over m, summation as this m small goes from 1 to m capital. And each node has nm data points. And on each data point, we have the loss FIM that is associated with it. So we want to find the model X that minimizes this average or finite subproblem. And we can only assume that we have access to FIM and its gradients at a certain point. So the algorithm that we have is called federated random reshuffling, and it is very simple. Um, we divide the optimization process into epochs, and on each epoch, we have um, we do one full pass through the data set on each device, and we do gradient descent steps during this pass. So, for example, but first we reshuffle the data. So, on device one, device two, device three, so on until device M, we reshuffle the local data, and then we go through the data and improve our model on each data point by using gradient descent. And then we average the resulting iterates. So this algorithm has been existent in some shape or form in software implementations, but it has not been analyzed theoretically before our work in the context of federated learning. So this algorithm in practice, it can do very well, as we can see here by the difference between FedRR and local SGD. And local SGD, also known as federated averaging, is one of the most widely used algorithms in federated learning. So clearly here, FedRR converges faster and also to a smaller error at conversions. Now, in the paper, which is Proximal and Federated Random Reshuffling by Konstantin, myself, and Peter, we give explicit convergence rates for our algorithm and show that its rate is superior to that of other baselines. And also, we study a lot more questions that are related to the general random reshuffling algorithm, which we instantiate here. So I hope that I got you excited to read the paper. So finally, this is a picture that I took around the time when I was in CAST in 2019. That I think it's the sunset is pretty beautiful, and hope that we can all be there after the COVID crisis is over. Thank you.